Hello everyone, I hope you are having a wonderful day. Today we are going to continue the discussion on the turbojet engines, essentially chapter 4 of the book, and we are going to talk about the UHP turbofan engines. And UHP stands for ultra high bypass. The concept is actually pretty simple, but they have started creating this type of turbofan engines very recently. I think the latest one was designed and manufactured sometime in 2013. So they are very recent engines. The reason is the manufacturing part of it is very hard. Of course, from the naming you can understand the bypass ratio. Let's say this is the core of your engine. The bypass ratio is very large, right? Compared to the regular turbofans. Well, why do we want to have an ultra high bypass ratio? Mainly because can reduce it can reduce fuel consumption by 15%. That's a nominal value, of course, and it also can cut noise by 20 decibel margin. So for commercial airliners, this is a very good achievement, right? They all want to reduce the fuel consumption and cut noise as much as possible. The bypass ratio here is getting very close to turboprops, which is going to be the topic from next week, right? So the bypass ratios that you're gonna see in these type of engines, it ranges from 10 to 35 to even higher, like 60, 70. Whereas in the regular turbofan engine, in the conventional turbofan engine, you're gonna see the bypass ratios of 6 to 8, right? But the question becomes, how do they reduce the fuel consumption? To answer that question, you have to be able to answer another question. What happens when you increase the bypass ratio? The main thing that happens when you increase the bypass ratio is then increase in the thrust power. Which means that your propulsive efficiency also increases, right? But these were not the goal. The goal was to decrease the fuel consumption, or TSFC. So if you go back to your notes, you're going to see that we have this equation for TSFC. V0 divided by QR. This is one of the many equations that we have. V0 divided by QR divided by eta P divided by eta thermal. So if you increase the eta P here, you're going to see an increase in the specific fuel consumption. So which basically means that because of the design parameter that you're including, because of the higher bypass ratio, you're going to get higher propulsive efficiency, and eventually you're going to get higher or lower TSFCs. But the question that may arise here is that, okay, so why haven't we done this before? Why is this a newer concept compared to the other jet engine concepts? There are some concerns that need to be addressed when dealing with new technology in general, and this specific one, right? The first thing that we had to address before being able to answer these concerns was to fix the operational disparity between the core and bypass. That's the first thing we needed to answer, because the core is going to have a much smaller diameter compared to the bypass, and that is going to introduce a lot of structural concerns in your design. So we should have been able to produce the material needed to being able to manufacture this, and a lot of concerns, right? And the other part is the gear system. So a higher bypass ratio means a larger fan, which is going to need a larger gear system. So you want to optimize your gear system so it won't be that large for your core, right? So we need to come up with a new gear system essentially that can handle this very large fan. Other than these two design concerns, we also have some installation concerns as well. The first one being the size of the fan. So the size of the fan is so big, or the size of the turbofan engine in general, this type of UHPs is so big that you need to be concerned about how you want to integrate this with wings or fuselage. You want to find the limit on the fan diameter you can have based on the designs of other parts of your engine. And also the nacelle weight here requires us to use composites, right? Because we want to reduce the weight as much as possible. Okay. There are a couple of other concerns that we don't want to get into. You're always welcome to read more about this. But I just want to introduce you to this new technology that's out there, the ultra high bypass turbofan engines. And the main concept, whenever you get a question that was talking about the ultra high bypass engines, your main concern is usually to calculate the TSFC and compare it to an older design and see how much of an improvement you will get. Okay, but the main topic of today's lecture is going to be the mixed exhaust turbofans with an afterburner. Keep in mind that I have prepared the PowerPoints for this lecture as well, and I will upload it on Blackboard, so you will have access to that PowerPoint before this lecture. So if you wanted to have the PowerPoint in front of you to be able to follow the lecture a little better, you are welcome to do so, and you can do that. So let's have a schematic of your engine and different stations. Let's start with station 2. That's your compressor inlet. That's your inlet, right? And from the station 2, we're gonna have a core as well as fan or bypass, right? A station 3 compressor outlet or burner inlet, a station 4 burner outlet or turbine inlet, and a station 5 turbine outlet, and the new states inlet, which we will talk about just in a minute, right? And your fan, you're gonna have a station 13, which is just after the fans, and then you have the fan duct, and here you are gonna get to a station 15, which is going to be the fan duct outlet. So we have the turbine outlet and the fan duct outlets. Okay. And this new additional part of the turbofan engine is called the mixer, which essentially is a location where the hot gas and the cold gas mixes, right? And we call this a station mixer. The station number, the outlet part of it is called 6M. And M here stands for mixer, right? And afterwards, we're gonna get the afterburner with the flame holders and the sprays, and you're gonna get the conversion diversion nozzle. So 7, 8, and 9. So the main focus of today's lecture is going to be on analyzing this part. A combination of station 5 and 15 as the inlet and the station 6M as the outlet. Okay. Let's see what we can conclude before even starting the analysis. Let's see if we can make any assumptions or if we can come up with any laws, right? Let's look at this, the pressure here, the pressure at the station 15 and the pressure at the station 5. Can we find any relationship between these two pressures? And the answer is yes, we can. So essentially we can rely on our understanding of the color condition, or the Kuda condition. Some people pronounce it differently. Okay? If you recall, the color condition told us at the trailing edge, when you have a trailing edge of an airfoil, the velocities are there must be 0 or must be equal, depending on the situation of the wing, right? Situation of the airfoil, right? We can make the same conclusion here, but for the pressures, right? So here, let me try to magnify this station 5 and 15. So you have the station 5 and 15. 5, 15. The pressure at this line here can be considered a trailing edge of the core. Okay, so at this trailing edge, in order for the continuity equation to hold true, these pressures P5 and P15 must be equal. So this is the first principle you are going to make sure you are considering when dealing with the mixed exhaust turbofan engines with an afterburner or without an afterburner. In general, with the mixed exhaust turbofan engines. Okay. So let's continue the analysis. As always, the first thing you want to do is we want to write the main equation. We want to find the main three equations. We want to find the mass conservation here. We want to find the momentum. And for our case, that's going to be it. We're not going to go to the energy equation. But the three main equations are always the mass conservation and the momentum equation and the energy equation. Okay. Before trying to write down the equations, let's see what we are dealing with. That's the first thing you want to always do, right? Again, let's look at the outlets. Station 15 here, station 5 here, right? And this part is essentially your symmetry line. So we are assuming symmetry axis. So we are assuming that your jet engine is circular and you can have a symmetry axis. So the cold air is coming in from the turbofan, right? We can always find a mixing zone. A mixing zone in which the hot air and the cold air are going to mix. But outside of this mixing zone here, you are only going to have the cold air, and here you are going to have the hot air coming out of turbine. But here you are going to have a mixed zone. So two different gases, keep that in mind. In the turbine, the gas that is coming out is fuel plus air. By the fan, that the gas that is coming out is only air. So in the mixing zone, we have a mixture. Let's call it the fan fluid, and mixture of the fan fluid and the turbine fluid. So the first question you need to answer before writing down the equation is that what is going to happen to m dot at a station 6m, at the exhaust of your mixer. Of course, the conservation principle tells us that m dot has to be the m dot coming out of turbine plus m dot coming out of fan, which essentially means that m dot coming out of turbine is going to be your core m dot naught, m dot naught plus m dot f, and the fuel is already added, plus your bypass ratio multiplied by m dot naught. So m dot 6m is going to be equal to m dot naught plus m dot f plus alpha m dot naught. So there are three things we want to find out. So this is your mass flux. We already have the mass flux. There are three other things that we want to find out. It's the pressure at the station 6m, the Mach number at the station 6m, as well as the enthalpy at the station 6m. Right. And we already have the mass flow. To be able to find these, we already know that we have to make sure that we have a good understanding of CP at the station 6M and gamma at the station 6M. Why? Mainly because we are at this exhaust of the mixer. We are dealing with a different gas, which is different from the fan, which is different from the turbine gas, right? So how should we deal with this? How should we find gamma or CP or other properties? The answer is very simple. For gamma, you essentially take the average of the two. So gamma 5 plus gamma 15 divided by 2 is going to be giving you gamma 6M, which for most cases gamma 15 is just pure air, so 1.4, and gamma 5 is air and fuel, so just add them up, you find the average here, right? But for CP, you need to find the weighted average of your whole system, okay? What does weighted average mean? Hopefully you know, but just to remind you, it's going to be CP at the station 15 multiplied by m dot f fan, which is alpha m dot naught, right? And CP at the station 5 multiplied by m dot of turbine, which is m dot naught plus m dot f, divided by m dot f plus m dot naught plus alpha m dot naught, which is going to be your total mass. Okay. And we also need to have a good understanding of the TS diagram. The TS diagram here is going to be different from what you have seen before. Let's look at this pressure line, the constant pressure line of P5, PT5, which is roughly equal to PT15. Based on our discussion, we know that after turbine, we have had some expansion, but the pressure, we still are dealing with hot gas, right? So the temperature is going to be higher than what you would see after the fan. There hasn't been any burning of the gas that is coming out of the fan. Okay? And these two get together in the mixing layer. Yeah, the mixing zone, right? It is also called the shear layer, right? Which means that the temperature at T15 is going up, right? So you have some heating happening here. But the temperature after the turbine is becoming colder and colder. Okay? So essentially this region is your hottest stream cooling down, and this region is your coldest stream heating up, right? Of course, they meet at a location which is going to be on another pressure line, constant pressure line, and that will give you the pressure, the total pressure at station 6, right? So we have two processes happening. It is not just one process in the mixer anymore, right? Because we have two inlets, two different gases are coming in. You have to make sure that you are clear about that one. Okay? So let's start with the conservation of energy. I don't know why I said we are not going to use the conservation of energy. Where's the first equation we are going to use, but that was my mistake. Sorry about that. So the conservation of energy essentially tells you that whatever energy is coming in is going to be equal to whatever that's going out, and there is no energy generation inside the system. It's just there is just mixing happening, right? Energy is coming in are m dot 5 out of turbine ht5. It's going to be equal to m dot 15 plus ht15. Okay. This is going to be energy going out. This is m dot 6m ht6m. Okay. Of course, we can divide all of these by an m dot naught and replace it with the equation with the relationship we have. We have the relationship of all of these with m dot naught. So this is going to be alpha m dot naught. This is going to be m dot naught plus m dot f, right? And this is going to be m dot naught plus m dot f plus alpha m dot naught, right? So we can divide this equation by an m dot naught and essentially get this 1 plus f multiplied by ht5 plus alpha ht15 equals to 1 plus f plus alpha multiplied by ht6m, right? And the only unknown here is going to be ht6m, so we rearrange the equation to give us the ht6m. 1 plus f ht5 plus alpha ht15 divided by 1 plus alpha plus f. Okay, so we have an equation for the enthalpy for the energy situation at ht6m. Of course, we can find the temperature using this relationship between the total enthalpy and the temperature, and that's going to be giving you the enthalpy at the station 6m. But we still don't know the pressure at the station 6m and also the Mach number. So to find the pressure and the Mach number, we need to write the momentum equation. Of course, we are only dealing with the one. That was one of the first assumptions we made, that we are only dealing with a one-dimensional flow. Okay, so we want to only find the x momentum, or the momentum equation in the x direction. Okay, let's do that. The momentum of the is going to be the momentum of the outlet minus the momentum of the inlet. Okay, and that has to be equal to the sum of the forces, right? The momentum of the outlet is m dot 6m. The velocity of 6m minus momentum of the inlet m dot 5 v5 plus m dot 15 v15, which is going to be equal to sigma f of x. All the forces that is going to be acting on this. But what are the total summation of the forces in the x direction here? We have the pressure forces, of course. The pressure force at the inlet is going to be P5A5 plus P15A15 minus the pressure force of the outlet, which is P6M A6M and also the viscous forces of the wall, which is going to be your wall, the integral of wall shear stress, the integral of wall shear stress with respect to the weathered area. Okay. This last term is actually the wall friction drag acting on the mixer wall. Okay, so we are only going to replace this with the drag, the friction drag of the mixer, df, d of f of mixer. And we also had the color condition here, which told us that P5 is equals to P15. We can also find the relationship for the areas. The area at 6M is area at 5 plus area at 15. So essentially your bypass area plus your core area. So let's rearrange the equation. Let's plug the forces in here in the main equation we had here. And let's rewrite the equation and see what we're going to get. We're going to get m dot 6m. We're going to take all of the terms we have for each station and combine them together, right? Get them together. So let's do the station 6m first. The momentum plus the pressure force minus the momentum of the and pressure force of the inlet minus m dot 15 v15 plus p15 a15, which is the bypass exhaust, right? And all of this is going to be equal to your drag force. So essentially you can find the drag force using this equation. So if what is going to happen to this equation if we assume that we are dealing with a frictionless flow? This term always goes to 0. That's the first thing that happens. Your friction drag will not be present in a frictionless flow, right? And if you recall from chapter 2, these terms are the definition of impulse at each station. So essentially we can replace all of these with the impulses. Impulse at the station 6m minus impulse at the station 5 plus impulse at the station 15 is going to be 0. So impulse at the station 6m is going to be equal to impulse at the station 5 plus impulse at the station 15. Okay. So what we are going to do is that we are going to assume that this is the case. This is what's going to happen. And eventually you're going to see that we are going to introduce a correction factor that is going to take into account the effects of the pressure loss due to friction, right? Okay, so transforming everything to impulse is going to help us tremendously, right? Because we are, based on, if you recall from the previous chapters, we had different equations for impulse. We had m dot v plus pa, and we had another variation, a dot rho v squared plus the pressure, right? Which essentially we expanded the m dot here and take the area out, right? Then we can also have another variation of this equation, which is a multiplied by pressure rho v squared over p plus 1. This essentially means that we are only taking the pressure out, okay? And if you recall, this equation, we have seen this in aerodynamics and previously in this course as well, is equal to 1 plus gamma m squared, right? It's a pretty simple analysis. You essentially use the ideal gas law to replace this as a function of temperature and R, and then we have the definition of speed of sound and so on and so forth. So you'll get to this equation. So your impulse is going to be equal to 1 plus gamma m squared, which means that multiplied by AP. Sorry, forgot about that one. That's a very important part of the analysis, right? So which means that you can replace your impulse with this, with this equation. So let's rewrite the equation again. You are going to get P6m A6m multiplied by 1 plus gamma 6m m 6m squared minus P5 A5 multiplied by 1 plus gamma 5 m5 squared minus P15 A15 1 plus gamma C m15 squared, right? So gamma C stands for this actually can be gamma 15. That stands for the gamma of the cold temperature, which is 1.4, and this is gamma of the hot temperature, which is or the like fuel included gas, which is usually 1.33. Okay, so we can divide everything by the area. One of the areas, we're going to choose the area of turbine to make this division, to essentially normalize the equation for the area. So the area won't be an unknown, and as long as we have the area ratios, we won't really need to calculate any areas. An area is a design parameter. This is never an unknown in your analysis, right? So essentially, and I'm going to replace A6m with A15 plus A5 and give you the final equation here, which is going to be our P of 6m multiplied by 1 plus gamma of 6m m 6m squared multiplied by 1 plus A15 over A5 minus P5 multiplied by 1 plus gamma 5 m5 squared plus A15 divided by A5 1 plus gamma C m15 squared. All of this is equals to 0. Okay, so we have an equation here, but the problem is we have two unknowns. We have P of 6m as an unknown and M of 6m as an unknown. So we only have one equation. What should we do? So we have to find another equation that's going to help us in this analysis, right? And that equation is going to be your conservation of mass equation. And we already have different forms of m dot. We know that we can calculate m dot using rho AV or AVP over RT or gamma P AM over the square root of RT of T, and eventually we can simplify this by gamma P AM over the square root of gamma RT of T multiplied by 1 plus gamma minus 1 over 2m squared. So what does this equation tell you? It tells you that if you write the conservation of mass equation, your only unknowns is going to be your Mach number as well as the pressure. Okay, so we have our solution, right? We have one equation, the momentum equation, and the other one we want to derive is going to be your conservation of mass equation. So the only thing you really need to do is to write the mass balance, which is going to be the mass of 6m is going to be equal to the mass of turbine coming out and the mass of fan coming out, right? Your final equation is going to be looking like this. It's just a plug and track, so hopefully you can do it by yourself, do the plug and track part by yourself. But essentially it's going to be P of 6m, m of 6m multiplied by 1 plus gamma of 6m minus 1 m 6m squared divided by 2. That's under the square root symbol, and we have the square root of gamma 6m r 6m tau t of 6m multiplied by 1 plus a 15 over a5. We have already normalized for areas. You may want to ask, what is going to happen to this term, right? Because this was one of the things that we were looking for. And if you recall from the conservation of energy, we were able to find this already. So this is not an unknown here. This is already a known parameter. So all of this thing is going to be equal to P5 M5 plus gamma T minus 1 M5 squared over 2 divided by the square root of gamma of T R of T TT5 plus P15 M15, exactly the same equation, it's just for station 15, gamma C minus 1 M15 squared over 2 divided by the square root of gamma C R of C TT15 multiplied by A15 over A5. Okay, so this is these two equations, this one as well as this one are going to be your two main equations that you need to solve to find the P and M5. And we are going to see this final solution for this, so you don't need to solve them yourself. But we are going to get them a little bit later. But at this point, you essentially have whatever you need to solve this parameter. And the solution procedure of the cycle analysis always starts with the marching technique. And you already know what marching technique is. You start from station 0, go all the way to station 9, right? Which is going to be your eventual station. But for each station, you want to see what we need. The first part is going to be a flight condition. In the flight condition stage, you always want to have the Mach number, the flight Mach number, the static temperature and pressure, flight altitude, and that's it. Or essentially, you either need the flight altitude or temperature and station. So this is an either of one of these will help you, because you should be able to get the temperature and pressure from the flight altitude, right? We have all of the tables for it. Then you get to the inlet, And for the inlet, you need the inlet adiabatic efficiency and the pressure ratio or the pressure recovery parameter, which is going to be your eta d or pi of d. Then it will branch out to a fan from inlet. So we have two different branches here. For your fan, you're gonna need the fan pressure ratio, pi of fan, all as well as the bypass ratio, and its a small stage efficiency. If you recall, we defined fan, we analyze fan as a compressor. So we have whatever we have in a compressor, we have it here as well, and all the definitions and equations are the same. So the polytropic efficiency or the smaller stage efficiency, or it's adiabatic efficiency of the fan. Because we know these two are already related based on the compressor equations that we have seen, right? And then you have the compressor. For the compressor, you're going to need the pressure ratio, of course, and the polytropic efficiency or the adiabatic efficiency. Okay. Then you have the burner. In the burner, you want to make sure you have, or the combustor, you want to make sure that you have the pressure ratio, the efficiency of the burner, as well as the ideal heating value, right? And you either want to have the turbine inlet temperature or the fuel to air ratio. And we already have seen all of the equations for this, so hopefully you are following. Then we have the turbine. For the turbine, you need to have the polytropic efficiency or the adiabatic efficiency, E of T or eta of T. Here we need a mechanical efficiency as well. The mechanical efficiency is the relates to the loss that you're gonna see in the gearboxes because of the power transfer to the fan and the compressor, right? And you need to have the turbine's exit Mach number, as well as here for this specific case, let me mark it with red, the color condition for your assumption, which tells you that PD5 is equals to PD15, or the same thing is true for the static pressure. Okay. Then here you're gonna get to the mixer. For the mixer, you need the viscous loss parameter that I mentioned, but we haven't seen yet. Okay. And the other things that we want to have is essentially we have to calculate the other things that we have. Then you get to the afterburner. And for the afterburner, you want to have the afterburner efficiency, the maximum temperature you can get, the design maximum temperature, TT7, or F of afterburner. Both of them work because we have the relationship between the two, and as well as the pressure ratio. And something that you need to make sure you have is the ideal heating value for the afterburner's fuel. So here you want to make sure that whether you are using the same fuel or not. If not, then you have to have an ideal afterburner here. Okay, and eventually you get to nozzle. For nozzle, we are going to need an adiabatic efficiency. Adiabatic efficiency or eta of nozzle, or its total pressure parameter. Okay, we also need to have the nozzle exit pressure, or the area ratio. right? We have gone over all of these parts, so hopefully at this point you have mastered the process. And eventually, you want to talk about the solution procedure. The solution procedure is always starts from station 0. You have the relationships between the pressure ratios, the total. Let me actually remind you of the relationships, like for station 0, for example. And these are all there in the slides. But since we have gone over these many, many times, I think you already know what I'm talking about. So this relationship is going to help you a lot. Is going to be equal to 1 plus gamma c minus 1 over 2, and this gamma c is 1.4. The cold part of the engine is gamma, right? M squared m naught squared to the power gamma c over gamma c minus 1. And we can have this equation for T naught, okay, which is going to be equal to T naught over 1 plus gamma c minus 1 over 2 m naught squared. And there's no power here. But based on that, you can find the pi of r, tau of r, and the speed of sound and everything else that you may need. You're going to use the same analysis for the compressor if you want to convert the total pressure to static pressure and vice versa in the inlet, sorry. And then you have the relationship between the pressure ratios or the between the pressure ratios and the temperature ratios and so on and so forth. But to give you an example, like for compressor, the pressure ratio, the temperature ratio is equal to the pressure ratio to the power gamma c minus 1 over gamma c E of c, okay? So we have seen all of these equations before, but they are also as well in your PowerPoint. So whenever you were dealing with this type of problem, you can just come to the lecture here. I have the full solution procedure for you. You can just go over it and find the equation you need, and you should be good to go, right? So it's just a combination of all the equations that we have, right? But then we'll get to the mixer part. We have the main equations, but we don't have like quick equations like we do for the other parts, right? We still have to solve two equation, two unknowns system and find the solution for it. But luckily we have done that for you guys, so you don't really need to find the solution. Okay. And for station 6M, I'm just gonna give you the final equation. But the proof of these equations are already in your book, so you don't need to. If you were interested, you can go back and read it, but you don't need to like memorize the solution. It's a pretty simple solution, right? I'm pretty sure you already can solve the system. It's just there are a lot of parameters that is going on. It is possible that you make a mistake there, but the procedure is already there. Now, I'm just going to give you the final solutions here. And the final solutions themselves are actually pretty extensive, right? So your Mach number, m6 squared, is equals to a constant c, and we're going to see what that constant c is, minus 2 gamma 6m minus the square root of c, that's the same constant again, minus 2 gamma 6m squared minus 4 gamma 6m squared. I'm just going to continue the rest of this on another line, right? so that we have, let me actually change all of this, or I can just move. Yeah, that's the better solution. Gamma 6m squared minus c multiplied by gamma 6m minus 1 divided by 2. Okay. And all of this is divided by 2 gamma 6m squared minus c gamma 6m minus 1. But how can we find the c? This constant here. C, the square root of this c is equals to c1 over c2, which are the constants of the system that we have seen, that we were trying to solve. But what are the c1 and c2? The c1 and c2 are essentially, they have very large equations and are functions of the Mach numbers at station 5 and 15. So let's do c1 first. c1 is equals to 1 plus gamma t m5 squared plus a15 over a5 multiplied by 1 plus gamma c m15 squared. All of this is divided by 1 plus a15 divided by a5. So this is going to give you the c1 parameter, and all of this is actually, this is also equal to p6m divided by p5 multiplied by 1 plus gamma 6m m6m m squared 6m, right? But using these you can find c1 here, the constant c1 here. One question you may have is about the area ratios. We have never seen an area given to us, so it is possible that we won't have the area ratios. How can we find the area ratios? It's pretty simple. a15 over a5 is related to m15 dot over m5, right? Because we already know that this is rho a v, right? M dot is rho a v. So if you go over it and do the calculations, you're going to find that you can find a15 divided by m dot as a function of your bypass ratio over 1 plus f multiplied by the ratio of the gammas and the speed of sound at the two locations multiplied by m5 and 15, right? And you're supposed to have all of these when getting to the mixer solution. So if you end up not having this area ratio, you can simply calculate it, right? Okay. But how can we find C2? Right? This is getting a little complex and confusing. So let me go back. We are trying to give you the final solution for that system of two equations and two unknowns, right? We have one of them as a function of a c, a constant c, and that constant c is equals to c1 over c2. A square root of that constant is c1 over c2. c1 can be calculated using this equation, and c2 can be calculated using this equation. Gamma t over gamma 6m multiplied by m5 divided by a5 plus gamma C over gamma 6M multiplied by M15 multiplied by A15 over A5 divided by A15. And all of this is multiplied by the square root of gamma 6M minus 1 CP6M TT6M, all of this under the square roots, over 1 plus A15 A5. This equation is also the line equation, the same as the C1 equation, but essentially you should have all of the parameters already for C1 and C2. Okay, if you ended up not having the area ratio, this is your equation. So using this, you can find the square root of C like that in this equation here. And you will get your Mach number at the exit of the mixer. But how can we find the pressure ratio or the pressure, right? P of 6M divided by P5 is going to be equal to C1. This equation is a little simpler, so that's good news. C1 divided by 1 plus gamma 6M M6M squared. That's it, right? But we don't really deal with static pressures that much here, right? So we need to transform this to the total pressure. We want to have this ratio. We want to have the pressure ratio, essentially PT6M over PT5. And the pressure ratio is defined by the ratio of the mixer divided by the pressure of the turbine, right? And we already have the relationship between the total pressure and the static pressure. This essentially is going to be, this ratio is going to be equal to this ratio multiplied by 1 plus gamma 6M minus 1 M6M squared divided by 2 to the power gamma of 6M over gamma of 6M minus 1 divided by 1 plus gamma of turbine minus 1 M5 squared over 2 gamma T over gamma T minus 1. Okay, so we are going to call this pi of mixer, the pressure ratio of mixer. But keep in mind that we didn't include the friction losses. So this is going to be your ideal pressure ratio of the mixer, right? To find the actual pi of M, if you recall, we are going to have a correction factor, which is, so this is pi of Mi, the ideal pressure ratio, multiplied by pi of Mf, right? That stands for friction, right? Pi of M, then you have friction. And this is going to be your correction parameter. I don't know, you don't need to calculate this. It usually will be given to you guys, right? So that's going to be your mixer. When you have the information of the mixer, you go to the afterburner, you calculate the afterburner properties, then you go to the nozzle and you calculate the exit velocities, and you can eventually end up finding the thermal efficiency, propulsive efficiency, TSFC, a specific trust and so on and so forth, right? I will probably upload another lecture, another recording of this lecture, and we'll go over one of the examples of the book as far as this is concerned, this type of turbofan engine is concerned. But that's it for the discussion. And as you have seen in the email, there won't be any quizzes this week. Those of you who essentially solved the example problem in the class, you can submit your answer to that example problem as a solution to the quiz for next week, right? And I will upload the homework by Friday. This homework is going to be a little more extensive than the previous one, because we haven't had a homework for, I guess, 2 weeks, right? So that is going to be it for the lecture today. Sorry I couldn't make it to class. There was, I think I mentioned to some of you guys that I have to leave to Maryland, but I had to leave a little bit earlier, so that's why I had to cancel the class today. And that is going to be it.